So now let's go back to the reason we started doing binary search trees in the first place. Efficiency. How efficient are the implementations of our search, insertion, deletion? So each of these kind of have the same structure in that they all have just one recursive call inside the recursive step. And specifically, they're using the fact that we have this binary search tree property to decide which subtree to go to. Let's focus specifically on contains for the moment, finding something. So here's our code for contains, which we've already seen. Each recursive call that's made goes down one level into the tree. So the maximum number of recursive calls that can be made when we do a search in a tree is equal to the height of the tree, which remember is the distance from the root to the leaf. Now technically it's that number plus 1 because there's an extra call since our implementation specifically is recursing into the empty subtree. But when it comes to some of these complexity discussions, the little like off by 1 things don't tend to make a big difference. Since each line of code inside contains other than the recursive call is constant time, meaning doesn't matter how big the tree is, the total running time is proportional to the number of recursive calls we make. Because we argued that the maximum number of recursive calls is the height of the tree, we could say the running time is big O of h, where h is the height of the tree. But this is only partially correct. In fact, if we get lucky and search for the root item, doesn't matter how tall it is, we make one comparison and we're done immediately. So far in this course, we've mainly focused on how running time depends on size of inputs. However, it's very often the case that for a fixed input size, the running time is based on other things to do with the input. For instance, looking for the root of a binary search tree versus something that's all the way one of the leaves of the binary search tree is going to have an impact on the time, right? So it's incorrect to say that the time to search a binary search tree is always equal to h plus 1, where h is the height. Really, h plus 1 is the maximum of a set of possible running times we could have. So this is where we get into what's called worst case running time. And we can define this as some function of n, which takes an input size n to the maximum running time for any possible input. In other words, what's the worst thing that could happen if you tried to run this algorithm on an arbitrary input of size n? So what we call the worst case is actually a family of inputs, and there's one of these per input size, which always is the worst for that size. So we could say the worst case for binary search tree contains is basically when the item we're looking for makes us recurse all the way to the deepest leaf in the tree and then search an empty subtree. So this is not just a specific size, this is for any size of tree. This is still just a rule, a property in common of all these sets of inputs, looking for the leaf at the bottom. Since the worst case running time is a function, we can describe it with big O. And we can say for binary search tree, the worst case running time is O of h, where h is the height of the tree. Similarly, best case running time is a function which is for the minimum possible runtime for the input size. So you can probably imagine for this one, the best case is that the root is what you're looking for. Since contains returns immediately, since it verifies, oh, the root is what you found, the best case running time is big O of 1. It doesn't matter how big your tree is. If all you needed to find was the root, it's right there. Now, when defining best case or worst case situations, you cannot make assumptions about the size of the input. So something that I hear commonly from students is, oh, the best case is when the binary search tree is empty. But this isn't a definition of best case because that only is true for a very specific input size, exactly 0. Whatever properties you're giving for your best or worst cases must apply to any size of input that you're working with. Now, you might look at big O of h and recall that we said searching through an unsorted list takes big O of n, where n is the size of the list. Since these look linear, it might seem like binary search trees haven't actually improved that much than unsorted list. And so this is where our choice of variables makes a difference. So we can say that binary search trees search, in the worst case, is proportional to the height of the binary search tree. But remember, the binary search tree's height could be a lot smaller than its size. Now, if we consider a binary search tree with n items, the largest height we could possibly have is n. In this case, the binary search tree is just a list, right? You only have one direction that you go all the way from top to bottom. But it could be as small as log of n. Why? Think about this another way. A tree of height h can have at most 2 to the power h minus 1 items. This is a bit of a bold statement. You should try drawing some examples to convince yourself what I'm saying is true. This means if you have n items to store, you need at least log n height to store all of them. So if we can guarantee our binary search trees have a height of roughly log n, then all of our operations, search, delete, and insert, have a worst case running time of O of h, which is big O of log n, where h is the height of the binary search tree and n is the size. Even for sorted lists, for which we use binary search and find items in big O of log n time in the worst case, they are still limited by insertion and deletion at the front, as we mentioned earlier in the course. Binary search trees are not affected by this limitation. It doesn't matter where the item needs to be inserted, it just matters what the height is. Now, unfortunately, what we've gone over in this course for insertion and deletion does not guarantee that modifications to the tree will keep it log n in terms of size. One example that you'll explore in the lab when you insert into a binary search tree is when you insert into a search tree in sorted order, and you get the unfortunate lists output. However, later on when you take CSC148, you will explore more sophisticated insertion and deletion algorithms which do ensure that logarithmic height is maintained, which guarantees efficiency of all these operations.